Okay, I think we'll go ahead and get started. With again, I'll announce that there's Alex. Okay, there he is. It's going to be lecturing again at 3:45, continuing his first lecture. Funny. Okay, anyway, it's a pleasure to have Giulia Semeghini, who many of you may have seen the public lecture yesterday. Tell us about quantum simulation and information processing for Rydberg atoms.
Okay, thank you for being here. I think this is your first experimental lecture of this summer school, so we'll see how it goes. I saw yesterday there are very few experimentalists in the room. Is that right? Can you raise your hand again? Okay, 3, 4, 5. Okay, very convinced experimentalists on the back. Okay. So anyways, these are going to be experimental lectures. And I think, even if the majority of you are theorists, I think it is good, especially if we want to work together, that you understand how these platforms work so that we can really try to make something together. So I will try to go fairly deep into the experimental details, just so you understand how these things work. But okay, so here there's not going to be any blackboard. I'm sorry, doing experimental talks on the blackboard is very difficult, but there's going to be some annotations, I think. Okay, so again, in these weeks, you've been hearing about a lot of interesting ideas. And in these lectures, we're going to look at an experimental platform where we can start to look into how we can implement these ideas, some of these ideas. So in particular, in this specific type of experimental platform, we are trying to achieve 2.5 broadly defined goals. We're looking into, so the main applications that this type of platforms can have are quantum simulation, quantum information processing, and quantum metrology that I'm counting as half because I'm not going to talk about it. It's a very interesting application of this platform, but I don't have time to talk about all of this. So we're going to mainly concentrate on these two things: quantum simulation of different many-body problems and quantum information processing. Okay, so the first thing that I want to do is to ask you, given the things that you work on and the things that you've heard about in these days, what do you think are the requirements for a quantum platform, especially thinking about these two goals? We want to do quantum simulation and quantum information processing. What do you think our platform needs? What are the requests? What's your grocery list for the platform that we want to use? So another way of thinking about this is, how do we choose the building blocks for our quantum machine? So here I'm gonna open the discussion to you, and we're gonna write them down and then see if the platform we talk about, satisfies some or all of none of them. Okay, so I'm gonna write them down as you say them. Let's see if this works. Okay. Who wants to start? Yeah. Okay, you're gonna go with that. I mean, before being scalable, but okay, let's write it down. Okay, scalability. But before that, okay, before scaling, no, it's okay. Yeah, long coherence times. I mean, okay, yes, let's write it like that. You're going too fancy. You need to think about, Okay, yes. Okay. To do logic, let's say, and read out. Okay, what else? Okay. Okay, so initialize into desired quantum states. Okay, what else? Yeah. Okay, this is the first, I would say. Okay, well-defined qubit. Okay. Well, yes, true. Yes. Okay. Interesting. Okay, what else? Sorry? Okay, good. Okay, anything else? Yeah? Connectivity. What about the connectivity? Okay. What else? Yeah? Okay. Okay, anything else? Okay, so let's look at them. Okay, what's the most important? I mean, let's say what's the first? What's the first? I already told you we need to have a qubit. Okay, maybe this is number one. Okay. Okay, long coherence times. Another way of thinking about it is you want this to be quantum for a long time, so you need to have good isolation from the environment. Maybe we can write it like this. And this is certainly very important. I would put it at 2. Okay, ability to do logic and readout. These are two quite different things, but I would say the ability to do logic has to do both with the fact that you need to be able to control the state of the qubit, the single qubit, but also you need to be able to entangle them and so do multi-qubit operations. So you need to have control at the single and multi-qubit level. So you need, yeah, okay, let's put it like that. Level. Initializing to desired quantum states, in a sense, is related to this one that we just said. You want to be able to control them, so this also implies initialization. Stability to find a temperature effect, it's more nuanced, is related to some of these other things. I think it still has to do, in a sense, with isolation from the environment, maybe. Individual qubit controllability is also important, the fact that you want to, it's also related to this control of single and multi-qubits. You need to be able to address them at will. Connectivity was a broad requirement. I think here, you want to be able to create entanglement, as we said. So you want to be able to do multi-qubit operations. But also, if you really were to wish for, the stars, you would say, I want to have arbitrary connectivity. So I want to be able to connect anything to anything. Mid-circuit measurements, again, is a little bit specialized. But again, if you want to do quantum error correction, for example, you want to be able to do that. Okay, let's see if I had something to add. Maybe one broad thing that I would say is that you want a lot of programmability, right? You want to be able to do different things on this quantum machine. You don't want it just to be specialized on one thing. That's good, but if possible, you would like to be able to do different things. Okay, so we're gonna leave it here, and then when towards the end we get back and we see how well we're doing with this platform on these requirements. Okay, so to start, I mentioned this last night as well for those of you who were there, but there are several quantum platforms that people have been looking at. So people have been writing down lists kind of similar to what we just did, and they looked for potential candidates to create these quantum platforms. And so there are different candidates. In this school, you're going to hear about several of them. So next week, you're going to hear about superconducting qubits and trapped ions. And there are 2 versions of neutral atoms that you're going to hear about. One is in these lectures, and another one next week as well. Okay, so in these lectures, again, we're going to concentrate on individual neutral atoms. So what's interesting about neutral atoms, and this kind of goes back to our list. The things that neutral atoms can do very well is it's easy to isolate them from the environment. So they have good coherence. They've been used in different contexts in physics for a very long time. So people know how to initialize, manipulate, and read out atomic states with very high fidelities. So this is good. We have the tools. And also, this is kind of more of a recent addition, but we also know how to turn on and tune strong interactions between neutral atoms using Rydberg excitations. Finally, going back, okay, then, we know that we can tune many different parameters in the system, which is also good in terms of programmability. And I think it's probably the thing that makes neutral atoms more special is the fact that scalability in these systems is a little bit easier than in most of the other platforms, in many of the other platforms, I say. So just to give you a sense, when people started to work on these atom arrays, the first implementation of this platform already had more qubits than any other platform that was out there. So this just gives you a sense that it was not because the people that were doing this was smarter than everybody else, maybe, but also because neutral atoms are just easier to put there in larger quantities. And I think we're going to see this in this first lecture today. Okay, so the outline of my lectures is the following. In the first one, we're going to talk about the platform. So we're starting kind of slow. I want to see how much you guys already know about this and try to give you the basics. And then in the second and third lectures, we're going to concentrate on examples of a few experiments that have been done on this platform. In the second one tomorrow about quantum simulation, and in the third one on quantum information processing. Okay, so we start with the platform. Okay, a little bit of history. The quantum platform that is based on Rydberg arrays is one of the most recent quantum platforms out there. It's about 7 years old, so we can consider it the baby of quantum platforms. But what I'm going to argue in these lectures is that it's a very smart baby, so it can do a lot of things despite its young age. So what was the basic idea at the origin of this platform? It was the creation of a new approach to generate large and ordered array of atoms. So there was another method that had been out there for a while that we're going to call a top-down approach, which is related to optical lattices. And here the idea is you have a cloud of atoms. Let's say that initially they're room temperature, so they're moving fast. You start to cool them down using different methods, and you try to cool them down so much that you can force them to occupy the minima of this optical lattice. So you have this crystal structure that you generate with lasers, and if you cool the atoms enough, you can have the atoms occupy the minima of this lattice, and so in principle you can have one atom per minima of this structure. And this is, for example, an image from these quantum gas microscope experiments, and you're going to hear a lot about it from Emmanuel Bloch's lectures next week, so I'm not going to tell you much about this. But you see, these experiments have been out there for a while, and they've made a lot of progress. And so you can see here that they can now do quite a good job at filling this lattice very well. So you see that most of the traps contain a single atom. You have only a few defects here and there. But this is a platform that is now working very, very well. But there is a second approach that you can use that we're going to call a bottom-up approach. So here you have a large cloud of atoms, and you try to put them down into this ordered structure. But the other thing you can do is you pick up one atom at a time, and you put them together to create your ordered array. And so this is the newer approach that, so this is, for example, an image of an array of atoms on a square lattice. And this is this new approach that has been developed starting in 2016 by 3 different groups around the world. And this is what we're going to talk about today. Okay, so what are the core ingredients of this platform? As we said, we were going to use neutral atoms, and I told you why. The second thing we want to do is to create a platform where we can have individual control and site-resolved readout. So there is an emphasis on the fact that we can control and read out individual atoms. And finally, we want to be able to have strong interactions between these atoms using Rydberg excitations. Yeah. Yeah.
So, can you comment on the disadvantage of the tweezers from the perspective of theory disagree? Like, you have different on the left one, density of the theory really is identical to the extent that Fourier transform an identical
Mm-hmm.
cell of identical right. In the tweezer space, there's some ability from
Yeah. Mm-hmm. Yeah, okay. So yeah, this is true. I think these two platforms operate in different regimes. So here, the spacing between the atoms is much smaller. So it's, again, since the lattice is created by interfering laser beams, then you have that the spacing is a fraction of a wavelength of the atom that you're using. Instead, in this case, the spacing is a few microns. You're really operating into different regimes. So I think the preference is really on what kind of physics you want to do. So for example, if you want to study anything that has some tunneling in it, going here is a bad idea because these traps are far away. As you say, there is some disorder between the traps, so having tunneling is really difficult. I think, yeah, as you will see from the experiments that we're going to show in the next day and the next few days, and comparing with what Emmanuel is going to show you next week, I think there is different set of goals that you can address with these two platforms. It is true. Here, it's much harder to have very uniform traps. It doesn't matter to some extent for many of the applications that you have here, but for some it does. Maybe I should, yeah, sorry. Yeah, exactly. So yeah, going back to what I was saying, if you want to have tunneling, it's very hard, not just because these are further away, but because to have tunneling, you want the depth of the two traps to be very homogeneous. And here, you know, the Beck's experiments can get to like a few % homogeneity across an array, but with lattices, it's much easier to have something that is really pretty flat. It is true. I mean, doing tunneling experiments here, it's very hard and people are trying to do it. Maybe I should mention that here in Boulder, actually, Alan Kaufman is trying to combine these two. So something that people are now thinking about is, can we take the advantages of these two platforms and put them together? So let's say we want to study tunneling physics, but we want to have the controllability and the tunability that is given by tweezer arrays. Can we do something where we put them together? I'm not going to talk about it, but just so you know, these things exist. Okay, so let's we were saying blah blah blah. Okay, so the crucial ingredient here for the first part to have this individual control is to use these optical tweezers. So I will tell you a little bit about how these work. These are just tightly focused laser beams. You want them to be so tightly focused that the volume inside the trap is so small that you can only have at most one atom in there. And I'm gonna show you a bit more about how this actually works. So as I was mentioning last night, this come from an idea that wasn't originally applied to atoms. It was applied to dielectric objects in general. And you use the light pressure from laser beams to trap the atoms. I will play the video in the background just so you can see that this works really nice for more macroscopic objects. Oh, should I let it play? Okay. Anyways, at some point you see these spheres that get trapped. But I think most of you have seen it. Okay. I'll give it 2 seconds. So here it's just the light pressure that can move the atoms, the dielectric objects, whatever they are, towards the maximum intensity of the laser beam. Okay. So this idea was first developed by a group in Palaiseau at the Institut d'Optique by Philippe Granger, where they tried to trap individual atoms in tweezers. And here the motivation was really what we're talking about today. How can we have this individual qubit based on neutral atoms that we can control, but individually? And so they realized that what you need to do is, so it was a challenge to be able to trap individual atoms. People had been trapping large quantities of atoms in dipole traps for a long time. But what they tried to do there was, okay, there are a lot of things here, but the important things is here at the center of this vacuum cell, there is a magneto-optical trap. Everybody knows what a magneto-optical trap is? Okay, ooh, Okay. Okay. It's a cold cloud of atoms. Let's put it like that. So for simplicity, let's just say that when you want to cool down atoms to low temperatures so that you can do this type of physics, you use laser cooling, right? So again, it's light pressure that is kicking the atoms from different directions so that you can slow them down. The magneto-optical trap slows down the atoms, but at the same time it traps them. So you have a magnetic gradient together with this rational light. So you cool them down and you trap them at the center of this magnetic gradient. But for what we care about today, it's just a cold cloud of atoms. So what they did here was they took a dipole trap beam. These are atoms of rubidium. So you shine these dipole traps, so this tweezer at the center of this MOT, and then you're trying to trap atoms from the MOT into the tweezer. So what they did here was to know if you are trapping the atom, you can shine rational light so that the atom scatters photons, and so you can detect the atom. And you collect the light both on a CCD camera, so you just take a picture of what's happening in the glass chamber, but also there is a photodiode, so you just count the number of photons that get scattered by the atom. And what they observed is something like this. So as a function of time, so the signal here is the background signal, okay? This one around 20. So what they saw is that initially there is no atom. Then they see that something happens. So it looks like an atom got trapped. But then, it goes down again to 0. It goes up and down a few times. But if you notice that it never goes above this value here. So it looks like it's a discrete thing. It's either 0 or something. And this something corresponds to one atom. And I'm going to try to explain you why it's exactly like this and why after we load an atom into the tweezer, then it also goes away. This is related to light-assisted collisions that happen in the tweezer. So the idea is the following. Okay, so what happens here is that, let's say at this point here, we have our tweezer with a single atom inside, okay? So we have the atom that is flowing around the tweezer. Okay, so let's say that initially it's here. It's, there is this cooling light that it's hitting the atom. And so this pushes down the atom into the tweezer. So what you see there, that signal corresponds to the single atom loaded into the tweezer. But what happens when the atom disappears is the following. So you have your atom into the tweezer. There is a second atom that goes down. So now you have the two atoms. And what happens here is an exoenergetic collision. So the atoms, for some reason that I'm going to explain in a second, get a lot of kinetic energy and they get kicked out of the trap. So as soon as you have two, they both get expelled from the tweezer. And this is related to this phenomenon of light-assisted collisions. So here what's on this plot is the molecular potential for the pair of atoms, right? You have these two rubidium atoms. This is the molecular potential. So this is the molecular potential when both atoms are in their ground state, which is the S state. Okay, so you have this pair of atoms. But now if you excite one of the two states to the P state, which is the excited atom, it's the excited state that you can excite with this cooling light, right? So we have this light at 780 that is the one that is creating the MOT. Okay, not if it, okay. So you have this 780 light, and this 780 light, it's close to this resonance, to this P state. Okay, so if one of the two atoms gets excited to the P state, now you find yourself on this other molecular potential, and you see that this one is attractive. It's much more attractive than this one. So when you have this pair of atoms in S plus P, they start going down. Okay, they start to attract each other. But then this atom in the P state is going to decay pretty quickly. The lifetime of the P state is about 20 nanoseconds. So after in a time comparable to those 20 nanoseconds, the atom is going to decay. So you find yourself again here. But then you see you've acquired a lot of kinetic energy in the process. And so you have your two atoms are now not trapped anymore in your tweezer. Just to give you an idea, in this tweezer, so these tweezers are about 1 micron wide, and the trap depth is about 1 millikelvin. But the energy that they acquire in this process is about 1 Kelvin. So this is much larger than this. Oops, you don't want to do that? Okay. It's much larger than this 1 millikelvin, and so both atoms get expelled from the tweezer. So this is why you can only have at maximum 1 atom in the tweezer, no more. But by doing this, what you end up having is that the probability of occupying your tweezer with a single atom at the end of a loading procedure is 50%. Okay, so you're guaranteed to only have 1 atom at the cost of, you don't have 1 atom all the time, because anytime 2 atoms go inside, they get both expelled. Yeah.
Can you say over time how the 2 atoms get excited? That's supposed to be.
So you have this near resonant light at 780 that you're using for the cooling. So for the MOT, you have that light. So that light can have a certain probability of exciting your atom in the S state to the P state, right? So you're moving now from this molecular potential to this one, where you have 1 atom in S and 1 atom in P, where P is the excited state. And so then when you have this pair, then you acquire the energy and then you decay again.
Different color of light.
Well, you would have a different transition, right? To cool, you need to be close to resonance to some transition in your atom. Yes. Sorry, I'm not sure I understood the beginning.
Then one of them absorbs a proton, then you S plus. But why can you not have the thing that both say S plus S?
Yeah, because the scattering rate from this light is very high. So the probability that one of the 2 atoms get excited is very, very high. That's why. Because you're very close to resonance, and so it's gonna happen that you acquire. And as you see in the experiment, you really see it. You never see the signal going up to 2 atoms. Yeah. Yeah, I mean, I think that could happen, but this is what happens first for sure. You immediately, I mean, this process is very fast. So, yeah. Yeah.
So you have this cold atomic gas, and then what happens?
Yeah. So, good point. Let's go back. Okay. So you have a tweezer is basically it's a trapping potential, and you're gonna end up in this tweezer if your temperature is lower than this trapping depth that you have here. So the tweezer is somewhere here. Let me draw it. So you have your tweezers that is focused somewhere in that vacuum chamber. The MOT is all around it. Okay. So as soon as an atom gets close to this tweezer, if its temperature is small enough, it's gonna end up in the tweezer. It's gonna. Okay. Yes. Mm-hmm. Yeah, it's yes, it's way less probable than this. Yeah. Yeah. Mm-hmm. Oh, what is this physics? Okay. There's a lot of atomic physics. Yeah. It's kind of an aside. We can talk about it. It's gonna take some time to explain this. Yeah. It's a genetic feature. I mean, just to tell you, this is a van der Waals type of interaction, and instead this has a different dependence because of dipolar interactions between the atoms. We're gonna talk a little bit about it later, but it's kind of different. Okay. Yes. No, it has some. You're still looking at molecular potentials, but not really. It's a different kind of process. It's a different process. In the van der Waals potential, you're tuning your molecular potential such that you have a resonance, and so you have strong interactions. Here, there is no resonance. So here, you're just exciting one of the atoms to this different atomic state, and that atomic state, the pair S plus P, has a different molecular potential. So they are more attractive than S and S. There is this magnetic gradient for the MOT, but it doesn't really matter. It's not really modifying this. You're close to zero field at the center of the trough, let's say. Okay, yes? Yeah, sorry, this arrow is in the wrong place. Yes. Okay, yes. Yeah, I cannot erase this, but okay. Yeah, delta is 1 Kelvin, yeah. Okay. Good. So we have this optical tweezer. What we want to create, so we understand how we can trap single atoms in one optical tweezer. But now what we want to do is create a one-dimensional array of tweezers. And to do that, we use an acousto-optical deflector, which is this object down here. What is an acousto-optical deflector? Here inside you have a crystal. And into the crystal, you input a radio frequency to create a phonon in the crystal. So what happens is that your laser beam gets deflected by a certain angle, right? You have your laser beam gets deflected by it interacts with the phonon and it gets deflected by a certain angle. If you change the frequency of the phonon, of course, you can change the angle. And so to create a one-dimensional array, what we do is we input different radio frequencies so that your single laser beam at the input gets split into different laser beams at the output with different deflection angles. Now, if you focus this with a proper optical system, you focus this array at the center of your vacuum chamber, you end up with an array of tweezers, okay? And of course, you can tune your radio frequency such that you have equal spacing, you can tune the spacing, you can do whatever you want. And again, what happens here is the same thing that I told you before. We have a magneto-optical trap that you know now is a cold cloud of atoms. You shine the tweezers onto that. And so you start loading the atoms into the tweezers. As I mentioned before, you have this stochastic loading at the beginning where you have a 50% probability that your tweezer is loaded with an atom and a 50% probability that your tweezer is empty. So of course, if you want to do anything interesting, you want an ordered array, right? So this is not ideal. So what you can do is you take an image of the atoms by doing fluorescence imaging. So what you're doing here is you're sending resonant light onto your atoms so that they scatter atoms. And you can collect the photons on a camera. And so you have an image of your atoms in the vacuum chamber. Okay, this is what it looks like. And so here you see this stochastic loading. You see that there are some empty traps here and there, but now you know which one are empty and which one are full. So what you can do is look at this image and feedback on it. So what we can do is let's remove those tweezers that are empty. We don't want them. And we can tune the radio frequencies corresponding to these loaded tweezers to rearrange them into an ordered array. So you move them around such that now you have your array of tweezers with equal spacing where all the tweezers are filled with a single atom now. Okay, so you see the second image that we take, it's a perfect one-dimensional array of atoms. Yes? Mm-hmm. You can sweep the radio frequency of that you send into the AOD, and so you're just moving it. So the position of the tweezer, up here comes from the deflection angle from the AOD, which comes from the radio frequency. So if I tune the radio frequency from smaller to larger values, I'm moving the tweezer. Yeah, those ones I turn them off, and then the ones that are empty but I want to move, I just tune the radio frequency to move the beam. Okay. So of course here you can decide what kind of array you want. So you can decide the spacing. You can decide if you want to have different groups of atoms and things like that. And again, as I was saying, this was the origin of this new platform. The idea that you can use a sequence of imaging the atoms and rearranging them to remove entropy from your system, right? Initially, you have this stochastic loading, you have some disorder, you can remove it just by imaging and doing a round of feedback. Yes? Cheap in what sense?
Well, like, eventually you want to use these atoms for something.
Mm-hmm.
So if like this step is much longer than the actual.
Good point. Good point. Let's talk about this later. Like, keep that question. I think as we go, you're gonna see. There is a limit. You don't want to do this too slowly, but you would see if that's the case. Basically, okay. Let me answer half of it now. So you have your atoms in vacuum, right? So these atoms are in vacuum. Your limit to the lifetime of your atoms in this moment is just vacuum lifetime, which means you're in ultra high vacuum, but of course you have something in there. It's not complete vacuum. So you have some chance that your atom is hit by one of these particles that are in your chamber, and so it gets kicked out of the trap. So it's dead, okay? That's his lifetime. So basically what you can see is that if you do this too slowly, you're gonna see that even if you were trying to do this and to have this perfect array, you end up with some holes anyways. And that's because during that process, these atoms were kicked out. So you were doing the right thing, but you were so slow that these atoms were dying for other reasons, okay? So you need to be sure that you do this faster than that, yes? The imaging is, so you shine resonant photons on your atoms, and you have this microscope objective. So it has a high NA. You collect the photons, and you project them on a camera. So this is really an image of your atom. Okay, so as I was saying, this was the origin of this new platform, these tweezer atom arrays, these tweezer arrays of atoms. These first works were in 2016, and these were the first things that people did just to show that you can create these defect-free arrays by using this type of techniques. Sorry, this is wrong. This version that I showed you was in 1D, but you can extend a similar technique to 2 dimensions and even 3. So these are examples. So here is a 1D example that I just showed you, but you can also do things in 2D. And so you can arrange the atoms into different geometries in a 2D plane. And the group in Palaiseau by Antoine Brouwer showed that you can actually do this in 3D. It's super complicated. They showed this and then they stopped doing it. But they can do cool things like the Eiffel Tower and stuff like that. It's really hard to use. So nobody really did science with this yet, but in principle, you can do it. Okay, let me just show you for a second how you can extend what I just explained you for 1D to 2D, which is what we're gonna use for most of the experiments that I'm gonna talk to you about. So when you want to create a 2-dimensional array of optical tweezers, you can do something different from what I showed you before with the AOD, with acoustic optical deflector, and use instead a spatial line modulator. So this is a different technique where you just use a holographic technique to create this pattern. So the idea is you shine your laser beam onto the spatial line modulator, which is this object. You imprint a certain phase profile on the laser beam, such that the Fourier transform of that phase profile is your desired intensity profile. Fourier transforms, even theorists are familiar with those. So this is just a Fourier transform technique. So you decide what's the phase profile such that the intensity profile in the focus of a lens is the desired thing that you want to create. Yes.
So the red lines that you draw,
Mm-hmm.
is this here, or is the thing that creates the lattice and the tweezers separated?
So the tweezers are here. What comes before is, yes, it's what makes the tweezers. But yeah, I would call the tweezers what happens in the vacuum chamber. What you have before is laser light that is gonna make the tweezers, but yes. Yeah, yeah.
Sorry, why can't you play this phonon cable?
I can, but I'm gonna show you in a second why I want to do this. We create this 2-dimensional array. Again, we do the same thing as before. So we create these this array, and then we focus it at the center of a vacuum chamber. We load the atoms into this tweezer array. So again, you see you have this random loading. We have about 50% probability of filling the tweezers. And let's say in this case, we want to deterministically fill a subset of these traps. We have 50% loading. So let's say we want to fill the half on the left. And these come the AODs and the phonons. Now what I do is I use a second set of tweezers. So here we have two sets of tweezers. One is generated by a spatial line modulator, and the other one is generated by acousto-optical deflectors like before. The only difference is you need two now, because you want to be able to move the AODs both horizontally and vertically. So you have two that deflect the beam both in the vertical and the horizontal direction. And these are tweezers that are easy to move now, because you can play the same trick that we played before. You change the frequency so you can move the tweezer on the 2D plane. And the way we use them is the following. Let's say that we want to fill this set of traps. We shine this other tweezer onto one of the atoms that was loading on the right that we want to move. And then we sweep the frequency of the acousto-optical deflector to move the atom across the array and drop it off at a final location that was initially empty, but we want to fill, okay? So we do this, and we can do it in parallel over many atoms at the same time. And so the final result looks like this. So now we've moved most of the atoms on the right to the left. And here we have an almost perfect array. We only have a few defects. So if I show you on average how this works in the experiment, you see that we can do this with pretty high fidelity so that we have an almost defect-free array. If you wait long enough, you're going to have some repetitions where you really have zero defects. Going back to the question about the lifetime of the atoms, we can do this with reaching about 99% filling of the final traps. The only limit, that 1%, is related to vacuum lifetime. Okay, so we do this in about 100 milliseconds. The lifetime of the atom is about 10 seconds in vacuum. So you have some chances that your atoms get kicked out of their traps while you do this. And of course, if you increase the numbers and the number of atoms, you have an exponential probability that one of them gets kicked out, right? Yeah. So this is 300 that you see here. I think the maximum we've done with the rearrangement is like 500. We've seen arrays that I'm going to show you a picture later. We've seen arrays with about 1,000 atoms, but we haven't rearranged them yet because there are some, just the software that we developed for this was not able to handle it. Yeah, so the lifetime is you have some probability that the atoms get kicked out. If you increase the atom, the probability that one of them gets kicked out increases. I don't understand the question. I mean, there are several limitations. You need a lot of laser power. Each of these traps requires, let's say, 1 milliwatt of power. So if you want, each of them requires 1 milliwatt. There are some limitations in the power that you have and the laser power, but also the lifetime is a limitation. If you start to go too big, then you have too many defects. You don't really win. That's true. Okay. So the nice thing about this procedure that I showed you is that it's very programmable. So you can put the atoms into different geometries. So these are a few examples of what we did in 2D. You can really do anything you want. If you want a random lattice, you do that. If you want different geometries, you can do it. You can really do anything. So this is the image with 1,000 atoms that I promised. So these are 1,000. We haven't been able to arrange them yet because of some stupid limitations in the software, but we're gonna get there. So now we've seen how we can have individual control and also this site resolve readout. With arrays with a few hundred atoms, potentially we can go up to about 1,000, I think, fairly soon in the next few years. Going beyond that, it's a different issue, and we're gonna, if we want, we can talk about it later. But now let's see how we can implement strong interactions between them using Rydberg excitations. So as I said, the distance between atoms in these arrays is typically a few microns. So these are neutral atoms, they don't naturally interact. So what we do is we use an optical transition to excite the atoms to a Rydberg state. So as I was mentioning last night, this means that you have the valence electron of your alkali atom that is promoted to this high orbital, which is far away from the nucleus. And the nice thing of these Rydberg atoms, of these Rydberg states, is that they have very long lifetimes. So you have hundreds of microseconds of lifetime, which is, it's long enough, as we're going to see. And you also have a strong dipole because of this large distance between the electron and the nucleus. And so when you have two atoms in these Rydberg states, because they have this strong dipole, they have strong van der Waals interactions. And this scale as 1 over the distance to the 6th power, as typical for van der Waals interactions. And you see here there is a huge dependence on the principal quantum number n, to which you promote the electron. This scales as n to the 11th. So as the higher you go, the stronger these interactions become very quickly. So just to give you an idea, if you have atoms that are between 2 and 5 microns away from each other, then the interaction strengths are between tens of megahertz to gigahertz. So the typical interaction times are much, much smaller than this lifetime of 100 microseconds. So you're in a sweet spot where you have strong interactions that happen on fast time scales that are much faster than the lifetime. So you can use this to actually have interactions between the atoms, entangle them, and so on. So the typical way in which we use these interactions is the following. If you look at a pair of atoms at a distance r from each other, here are the states for the pair. So you can have both atoms in the ground state, one atom in the Rydberg, or both atoms in the Rydberg state. If you have this optical transition that we drew here, then you can excite one or both of them to the Rydberg state. But if you put the atoms too close to each other, then you have an energy shift of the doubly excited state given by this van der Waals interaction. So it goes down with 1 over r to the 6th, but at short distances, this is a huge energy shift. And so at short distances, you can no longer excite both atoms to the Rydberg state. It's not energetically allowed anymore. And so you have this phenomenon that is called the Rydberg blockade, which simply tells you within a certain distance, you can have at maximum 1 excitation, because those are the other atoms within their radius are so shifted in energy that they cannot be excited anymore. And this typical distance is given by the blockade radius, which is defined by this condition that the interaction energy is of the same order as the Rabi frequency omega. Okay. Now we want to be able to excite to the Rydberg state. Yes?
Sorry about, I probably said it and I missed it. What is the dotted line below the Rydberg state?
It's the tuning. I'm going to talk about it later. It's so important now. I shouldn't put it there, actually. Good point. Okay, yes? You need to add the tuning. You need somehow to compensate for this energy difference. And so actually you can do it with this. If you go above the Rydberg state with a positive detuning, you can compensate for this energy difference. Why should you go out of the trap? You can, I mean, yeah. It doesn't have anything to do with this, but you can send it out of the trap, and actually it has to do with the Rydberg, but yeah, no, not for this. Okay, so as I was saying, we want to be able to excite to the Rydberg state in a coherent way, so to have coupling, to have coherent coupling to the Rydberg state. So let me just show you how this actually happens in the experiment. You have your array of atoms in 2D. And typically you want to couple all of them homogeneously to the Rydberg state. So you want all of them to have the same Rabi frequency and the tuning. So let's say let's consider now to have rubidium atoms, which is what we're going to talk about for most of these talks. We have our ground state and we choose a specific Rydberg state. In our case, it's the 70s 1/2 state. And to get to the Rydberg state, we are going to use a 2-photon transition. The reason why we use a 2-photon transition and not a single photon transition is that to go from G to R with just 1 photon, we should use a UV wavelength, and it's like 295 nanometers, which is very difficult to use and to have large powers. So most people use a 2-photon transition. So you go through an intermediate state, but you're far detuned from this state so that you don't really scatter the atoms through that state. And as I said, we want to have homogeneous coupling. So what we do is we shape two laser beams to be very large so that they cover the whole array, and they're pretty flat over the whole array. So there are two main ways in which people do it. One is you have a Gaussian beam, but you make it very, very large so that the part that the atom sees is just basically the peak where the intensity is almost flat. But doing that means wasting a lot of power because you have a lot of power in the wings that you're not using. Or what we do in our experiment, you can do some beam shaping. So you can use optics to have a flat intensity of your beam across the array. So for all intents and purposes, you can consider this as this optical transition with Rabi frequency omega. So in most of the things that I'm going to talk about, you will always see this seemingly single photon light transition. And we can drive Rabi oscillations between the ground and the Rydberg state. So you see that we are actually coherent. You can, go back and forth many, many times. But now going back to this blockade idea that I introduced before, what does this? So we have this type of interaction. We have these van der Waals interactions. So the Hamiltonian that describes our system when you have many atoms, let's say we have our atoms on a square lattice like here, the type of Hamiltonian that describes your system is the following, which is what we typically call a Rydberg Hamiltonian. So you have a drive term. So here you have your operator sigma x that couples G to R. You have and it's proportional to the driving, so to the Rabi frequency of your optical transition. Then you have a detuning term, and here it goes back to what this means. So you can choose if there is an energy mismatch between your laser beam and the transition here. So you can choose to have some finite detuning from the Rydberg atom. And so you have this detuning term where Ni is the occupation of the Rydberg state at a site I of the lattice, and delta is the detuning. And finally, you have these van der Waals interactions between atom in the Rydberg state. Okay, so this type of Hamiltonian corresponds to an Ising model because this term here is proportional to sigma x. So this is basically, to sigma z. So this is a sigma z term. But you also have a transverse field that is proportional to this term here, omega. And then you also have a longitudinal field, which is this other term here, okay? So this is the type of Hamiltonian that you can create when you use this type of van der Waals interactions between Rydberg atoms. And this is what has been used the most in this type of systems, is this Rydberg blockade effect with this type of Ising Hamiltonian. The reason why people really like Rydberg blockade is that it's extremely robust. We're gonna comment on it, in the next two lectures, but here, all you need to have blockade is that the interaction is very large. So if it changes a little bit, a few %, you don't care. You just want to achieve blockade. So if you have some disorder in your system, it doesn't matter. For most of the other type of interactions that you can have, it does. So the reason why people really like Rydberg blockade is that it's very robust. But of course, there is a limit. I mean, we can only do Ising model here. So the question is, can we access different types of Hamiltonians? So I'm going to show you that there are different things that people have been thinking about and trying in experiments to engineer different types of interactions between Rydberg atoms. Yes? So, so the higher the principal quantum number n, the larger is the interaction, okay? And the longer is the lifetime. So as if you go higher and higher, you get. But at the same time, the Rydberg states with high principal quantum numbers are also a little bit more delicate. For example, if you have some electric field noise, those states are very sensitive to it because you have a stronger dipole. So of course you're sensitive. You're more sensitive to these things. So typically it's a compromise between different things. So when this experiment at Harvard was first designed, they tried to go to 100. They saw that there was a lot of noise, so they went back to 70. It's a little bit of a compromise between different things. You don't want to go too low, otherwise your interactions are too small. Mm-hmm. Mm-hmm. So the separation between the different Rydberg states, even with different M, are a few gigahertz. So you can select one of them quite well, if just by tuning your frequency exactly there. Yes. Good point. So the way you do readout is, I'm thinking of just, okay. So it turns out that when you excite to the Rydberg state, your atom is no longer trapped in the tweezer, which it comes back to your question before. Basically, you have, so to be able to trap into the tweezer, you need a certain polarizability of your atom. And when you excite to the Rydberg state, you become anti-trapped because the polarizability changes sign. So what we do is, when we're exciting to the Rydberg state, we turn on the tweezers just for a very short time. So the atoms are kind of flying, but it's so quick that it doesn't even matter. You turn off the tweezers, you do the Rydberg excitations, and then when you want to do the readout, you turn on the traps again. The atoms in the ground state get trapped again. The one in the Rydberg state get lost. And so a loss corresponds to the Rydberg state. It's a destructive measurement for sure. We're going to discuss more about this probably in the third lecture, I think. But yes, this type of readout is super destructive. Yeah. Yeah. We're going to get there. We're going to get there. You're going too fast. Okay. Yeah. Mm-hmm. Mm-hmm. Yeah. So basically what you do, we're going to talk about this tomorrow, but basically what you do is you have your atoms like that. When you turn on the quantum dynamics, so when you turn on the Rydberg excitation, you just turn off the tweezers. So the atoms are flying, but they're not trapped. But the times in which they're flying is so short that they're not moving. So they're still on the lattice, right? They don't have time to move enough. And they're very cold, so they're not moving much. Okay, so you do your dynamics like that, and then you turn on the tweezers again to do imaging.
But like sometimes you display like images of antiprogmatic states.
We're gonna get there. We're gonna get there. When we take the image, they're trapped, but when the Rydberg excitations happen and the actually interesting quantum dynamics happen, they're not. Yeah. 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 I mean, the purpose here is that you guys see behind the curtains. I mean, there are a lot of things you typically don't realize. Okay, so let me just briefly mention. So we can do different types of interactions. So we've mentioned the Rydberg blockade. We said the Rydberg blockade has this dependence. You have 1/r⁶. This corresponds to an Ising Hamiltonian where you have ZZ coupling. I'm going to mention a few of the other things that you can do, and then I'm going to tell you a little bit more details about two of them at least. Another thing that you can do is to have dipole-dipole interactions. So these scale as 1/r⁵, and they can give rise to XY Hamiltonian, and I'm going to explain you how these work. You can also do Rydberg dressing. So you see here we've added at least one Hamiltonian. So here we had ZZ, here we add XY. Another thing you can do is to have Rydberg dressing. So here you're not actually exciting to the Rydberg state. You're just coupling off resonant to a Rydberg state to have some admixture of the Rydberg state in your ground state. And I'm going to tell you some details about this too. With this, you can access different types of Hamiltonian. You can do Ising again, but you can also do XYZ or a principle. That's the idea. It's not been done yet, but there is a proposal. You can do something very interesting. This has been introduced only in the past couple of years, I think. You can do ultra fast interactions. So here, if you excite your atoms using very short pulses, like 10 picoseconds long, you have that your whole dynamics is happening super fast, and you can go faster than the blockade. Okay, so if you go faster than the blockade, it means that you can excite both atoms to the Rydberg state and use so-called Foster resonances to have interactions between your atoms. And in the Omori group in Japan, they've used this to do entangling gates between the atoms. I'm not gonna tell you the details, but I'm gonna add the reference to the slide so that you can look it up. This is also very cool. The fidelities for those gates are right now not super high, but I think it's an interesting different idea that people are coming up with. And finally, you can do Floquet engineering. So here, I mean, this is not specific of neutral atoms. This is a general technique where using a periodic drive on a very fast timescale, you can create an effective static Hamiltonian that you want to implement. And this really gives you access to a broad range of Hamiltonians. I won't go in the details of these. Maybe I will show you some of these proposals in my talk tomorrow if I have time. But the idea is that you can really access different types of Hamiltonian. This proposal here, for example, is on how to use Floquet engineering to have an honeycomb XYZ model for spin liquid stuff. So I'm going to show you a little bit of this, but this is really very flexible with some drawbacks that are related to Floquet engineering. But there are ways that people are thinking about to go beyond Ising and be able to implement different types of Hamiltonians. Okay, so I'll tell you a little bit about these two, dipole-dipole interactions and Rydberg dressing, because these are the ones that have actually been done in experiments and have had some kind of success, or at least promise to be able to. Okay, so let's start with resonant dipole-dipole. So here we've seen how we can use laser excitation to couple the ground state to a Rydberg state. But what if now we add a second Rydberg state? Okay, so in these experiments that I'm going to show you, they chose the 60S, S1/2, and the 60P1/2. So you have these two Rydberg states. Now we're going to forget about the ground state. We're going to assume that we're always in the Rydberg manifold. And you can do excitations, coherent excitations between these two using this time a microwave pulse. Here, the distance between these two states is like 15 gigahertz or something like that. So you're in the microwave range. And so you see from this data here that you can indeed drive these coherently. Now, when you have two Rydberg states, if you compare, if you consider the atom pairs as P and PS, these are now degenerate, of course. And so you can have resonant dipole-dipole interactions between your atoms because of it. So let's say that we have two atoms at a distance r, so atoms A and atom B. We prepare the pair such that one of the atoms is in P and the other one is in S. Okay, so they're in opposite Rydberg states. Now, because of this dipole-dipole interaction, they're going to have flip-flop interactions. So the two atoms are going to swap the P excitation back and forth. And this is this resonant dipole-dipole interaction that scales as 1 over r cubed. Okay. So you can see this has been probed in experiments, again, by the group in Palaiseau, by Antoine Brouwys. And here what they showed was they prepared the pair in PS, so as I showed you here. And then they let it evolve, and they saw oscillations between PS and SP. So the P excitation was going back and forth between the two atoms. And what they showed here is that this actually scaled with as 1 over r cubed. When they changed r, they saw that this dependence was actually correct. So when you have this, you are the Hamiltonian that describes your system is this XY Hamiltonian. So again, you have the driving term with the microwave, you have your detuning term, and then you have these sigma plus, sigma minus, sigma plus terms. Okay, I'm gonna try to show you a little bit of an experiment tomorrow about this, but for now, this is the idea. Yes?
So all the atoms states, but you don't have the blockade happening.
So the blockade is between two atoms. When you have two atoms that are promoted to the same Rydberg state, here there are two different Rydberg states, so that there is no blockade.
And then these keys are fidelities.
Oh, yeah, sorry. So this is the probability of observing the state PS, and this is the probability of observing the state SP. Okay, so you're seeing that you're switching between these two. Yeah, so you have these two atoms. This is the probability that you have P on A and S on B, and vice versa, right? So you see that basically a way of saying this is that the P excitation is going back and forth from A and B.
There's a blockade in principle.
Yes, if you have another atom in S here and it's within blockade radius of this, you are not going to be able to do it. But if you notice here, R, the distance is 30 microns, so it's super large. So this is beyond the blockade for just S. Yeah, you're in a different region. Yeah. Okay, the interesting thing about this type of interactions is also that they are anisotropic. So you have an angular dependence. And so you can play some tricks deciding, what's the angle, the relative angle between the dipoles, such that you can tune also the amplitude, the intensity of these interactions. Okay. The other thing that I wanted to mention is the Rydberg dressing. So here, as I mentioned before, what we're doing is we're coupling off resonantly to the Rydberg state. So we have a large detuning, such that the ground state is weakly admixed with the Rydberg state. So what's the idea? We're in the weak dressing regime, where omega is much smaller than delta. Okay, so we want a very large detuning. When we're in this situation, we have a dressed, so-called dressed ground state, G tilde, where that is the sum of G with some of mixture of the Rydberg state. So you have a small admixture, beta, this coefficient is the ratio of omega and 2 delta, so it's a small number. And now, why is this interesting? It's interesting because with respect to the atom that is actually in the Rydberg state, the lifetime is extended. So let's say that the Rydberg state has a lifetime tau r. The lifetime of G tilde is tau r over B squared, or over beta squared. So it's much larger. So the initial idea of using Rydberg dressing is you use the nice feature of the Rydberg state, but you're not excited to the Rydberg state effectively. You only have a small admixture. So the lifetime is much larger. And so you have longer times where you can use this. Yes?
What is the word?
So basically, you have, well, admixture means this, that your state is the sum of these two. And so you have some, what this actually means for us now is that some features of the Rydberg state are in your dress state, even if you're in the ground state. Yeah. Well, it depends. So here I'm not talking of any particular experiment. This is in general what we are trying to do. Again, you're going to, I mean, it doesn't matter. I mean, you can tune omega and delta, whatever Rydberg state you choose. Omega doesn't have to do with the length of this air. Omega is proportional to the intensity. It's the coupling. So yeah. So here, this distance is the frequency, right? But omega is how strong you're driving. So how much you're coupled to this, to the excited state. Yeah, you want to be, you want to make sure that you're not coupling to other states. So, you need to be separated from other energy differences, but yeah. Is this more clear now? Okay. Okay, so here the key is the lifetime, okay? One of the reasons why people started to look into this is the lifetime. So as I was saying, if you do the admixture, it means that some of the properties of this excited state are transferred to the dress state. And in particular, you have some dipole in this dress state. And so you also have effective interactions between these dressed atoms. If you have two atoms in G tilde, they are also interacting. If you're at large distances, larger than a critical distance that I will mention in a second, then your interaction potential is basically the Rydberg interaction potential, so the 1 over r to the 6 that we saw at the beginning, the van der Waals, multiplied by the probability of exciting both atoms at once. So you have this beta square that is actually, taking your potential down. So these atoms are not interacting as strongly as if they were in the Rydberg state, but still they have some significant interactions. But if you are at small distances, you have the blockade again, okay? So what happens here is that you don't have the full 1/r⁶, but you have a saturation of your interaction potential at this particular value. So the potential here has this shape that is called a soft core potential. So you have the 1/r⁶, but then it doesn't keep going up. You have the saturation that I mentioned here. So this is the type of interaction that you can have between atoms that are dressed in this weak dressing regime. Okay, so what has this been used for? So far, this Rydberg dressing has been used to realize again an Ising model. And here is, for example, a paper where they did entangling gates using this dressing. But I think the reason why I wanted to mention it is that there are some interesting ideas that are being explored by Christian Gross group in Germany, where they want to use dressing to realize universally programmable analog qubit couplings. So the idea that they probed into this recent paper is a little bit more complex than this. I'm not gonna tell you the details, but you can look at the paper. Instead of dressing with a single Rydberg state, they dress with two. And by doing that, they promise to be able to engineer X, Y, Z type interactions. They show some results in that direction, but they see that there are no coherent interactions yet because of some experimental limitations. And here I just want to make a comment. I said before that the reason why people love Rydberg blockade is because it's very robust. If we go back to the resonant dipole-dipole, this is a very nice thing that you can do. And the group in Palaiseau has done a lot of experiments with this type of Hamiltonian, and I'm going to show you some of the results tomorrow. But what's the limitation here? Here you really care about the actual distance between the atoms, because if you change the distance, this coefficient C3 changes. Sorry, this R cube changes, and so you have some disorder in your Hamiltonian. When you're using the blockade, you don't care. And this motion can be because, as we were saying before, the tweezers can be moving a little bit, or their position can be a little bit disordered in the array, or there is some finite temperature in your atom, so they're slightly moving. And so this type of Hamiltonian is very sensitive to that. And I'm going to show you in the results tomorrow that they have limited fidelities because of that. And then if you look at this dressing, they have even stronger limitations, which is why this is something that has been explored, but hasn't been super successful so far because of similar reason. You have disorder, and that disorder matters. Yeah. Yeah.
The interaction.
Why do you add ZZ if you go to a different state, to a different N?
Yeah, because now energy of the possess is different. So there's a different repulsion.
Yes. I mean, here they've used this as a pure XY, so they don't have any Z. In principle, you can add the Z. I mean, even just staying here, if you put, SS and PP interactions, then you also have the blockade, right? So you. Mm-hmm. 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 Yeah, I mean, in principle, I think you can. It hasn't been done yet. They've done some other interesting thing like spin-orbit coupling using some similar tricks, but I don't think that that kind of thing has been done yet. I think it's a little bit tricky, but because here what you want to do is you want to be able to promote everything to the Rydberg state, and then you confine your dynamics into the Rydberg manifold. If you want to do something that is blockade plus XY, you need to do something different. So yeah, you want to be able to have all those terms. I don't know how well it will work.
Just SD fraction, where SD is the SD down to minus 1/2 one of the plus the other. This sigma plus and sigma minus is not.
No. This is yeah. I see. I need to think about it, how it will work, but I understand what you're saying. Yeah. I see. Okay, I need to think about how that would work, but I understand what you're saying. Yeah. Okay. Let me see. Yeah. So here, well, okay, we should look at the specific, different papers use different things, but typically you use two hyperfine levels in your ground state or something like that. One of the two is dressed and the other one is not. And then you do operations between them, and turning on and off the dressing, you have these type of interactions or not. That's the typical thing that people are doing. But as I mentioned here, for example, they do something crazier where you have a lot of states involved and you couple to two different Rydberg states. So it depends a little bit on the specific scheme, but usually you use you use your ground state manifold. You have two states that you use as your qubit states, and then you perform some dynamics there. It affects only one of the two states of your qubit. Yeah, but it's something you will see it in 2 days. We do something like that also with Rydberg excitations as well. I'll talk about it. Yeah.
Yeah, in this we see that the lifetime scale at beta square and the interaction scale at beta square cos power. This is a big problem of the lifetime.
Yeah, no. I mean, I think to be completely honest, this Rydberg dressing scheme has not been super successful so far, because it's really challenging to really be able to use the features of this scheme. People have been thinking about this Rydberg dressing for many years, but the results are fairly limited. I think so. As you say, also there are some scalings that you need to take into consideration that might be not super convenient, and the interaction strengths are typically small because of this beta to the fourth power. I think, to me, this application is the only very interesting thing that I've seen so far. If this actually works, and so you can really broaden the kind of Hamiltonians that you can do, then it's worth the work, because now you really can do different types of interactions, which makes things, even if the interactions are not as strong as you can have when you actually excite to the Rydberg. Yeah. No, but as you said, this beta squared and beta to the fourth, it's a problem. Okay. Okay, I'm almost done. So before concluding, let me just mention, I've showed you so far that these tweezer arrays have been developed initially and have been mostly used with single alkali atoms. So most of the things that I've shown you are with rubidium. Other people have used cesium, potassium, and so on. So the alkali atoms were the first and are probably now still the most popular implementation of this platform. But since then, people have become creative and have started to think about, can we use these tweezer arrays but to trap different kinds of particles with more complex degrees of freedom? And so, as I'm going to show you in the next few days, you can also trap alkaline earth atoms. These have a more complex and maybe a more interesting atomic structure because you have 2 valence electrons and you can do different types of things. And I'm going to show you what are some of the features of these types of atoms. People have started to use molecules, and this is something very interesting that is happening now because you can do something similar. So you see here, for example, this is an array of molecules trapped in tweezers. This is a recent experiment from Princeton. And here you can do some very interesting things. And I think there was a paper just last week about how people have put together actually also Rydberg atoms with molecules and seen interactions between those. So there are some new degrees of freedom that you can explore there. Another thing that people have been doing and that I'm personally doing in my new lab is to use atomic mixtures. So instead of having just one type of atoms, you have 2. And so here you see you have the blue and the yellow atoms. These correspond to 2 different atomic species. And so by doing that, there are some interesting schemes that you can use, for example, for quantum error correction, mid-circle readout, and things like that. So I'll try to talk a little bit briefly about that in the next few days. And I just want to mention one interesting thing is that since a few months, there is one of these programmable quantum simulator is also on the cloud. This is from the startup Quera that is in Boston, and it's kind of related to our groups at Harvard, which means that now people can start to run experiments on these type of platforms, which is something that I'm really looking forward to see what people come up with. You know, now it means that, you know, everybody can run an experiment on 256 qubits. So I think it's interesting to see what people are going to come up with. To conclude, I'm perfectly on time. I want to mention something that kind of opens to what we're going to discuss in the next few days. We often talk about these tweezer atom arrays as a programmable quantum platform. I've talked about how there is this programmability in the geometry, so you can arrange the atoms into square lattices, triangular, Kagome, whatever you want. I've talked about the programmability with interactions, with these different types of interactions that you can implement. But I think something that to me is particularly interesting about this platform is that you can really, it's well suited for different modes of operation. So you can use it in an analog mode where you really engineer the system Hamiltonian, you tune your parameters continuously to encode in your Hamiltonian some interesting phases of matter or some quantum dynamics and so on. But you can also use it very well in a digital way, where you really implement discrete layers of gates that can be single qubit or multi-qubits, and so you implement your quantum circuit to generate whatever desired entangled state you want. And also, kind of recently, we started to probe a possibility to do more hybrid types of things where you combine analog and digital together, and hopefully I'll be able to show you at least one example of this in the next couple of days. Okay, I think I had some more, but I think it's good to stop here. Okay, maybe let's go back to our initial slide with our list, and let's see what you think about it. Okay, there we go. Okay, so looking at this, I think we haven't discussed all of these things yet, but maybe you have a feeling of how well this platform can do in terms of the things that we've talked about. I commented about scalability. I told you that it's fairly easy to scale. Maybe I can comment now on this. I talked about the fact that it's fairly easy to go up to 1,000 atoms. Beyond that, we have 2 limitations. One is laser power, but you can say, okay, you can always, buy more lasers or, try to convince laser companies to deliver more power. One more fundamental limit to that scalability is given by vacuum lifetime, which is why people now are developing some experiments that go cryogenic. Going to cryogenic temperature can improve the lifetime a little bit. So that should allow us to go a little bit further. But there are still some very strong limitations, like to create this tweezer array, you're using a laser that goes through an objective microscope. And this objective microscope has some limited field of view. You cannot fit 1 million tweezers into that. So we're going to get to some fundamental limitation where I think we cannot get beyond 100,000 atoms. So beyond that, we need to be creative and find ways to put this together in some other fashion. Long coherence times, we're going to discuss this in the next few days. Logic and readout too. Initialize or well-defined qubit. I think we've got it with the ground and the Rydberg. We're going to have different types of qubits in the next few days. Okay, most of these things are going to be discussed in the next 2 days. The only thing that I mentioned so far is the programmability. You've seen some of it, and I think in the actual experimental implementations in the next few days, you're going to see how that actually works and how we can do different types of experiments with the exact same platform. So I think with this, I'm done 4 minutes early. Yes. Yeah. Good. If you have questions, I'm happy. Yes. Mm-hmm.
So in principle, there is no limitation to the qubits, right? Qubits.
Yeah. I mean, if you want, I mean, it's okay. The first question is, what is the? I mean, yes, people have been thinking a little bit about it. So, for example, a way of encoding qubit is you couple to different Rydberg states, right? So now you have three relevant states that are all coupled to each other. In my very limited point of view, I think, but to me, there hasn't been a strong motivation yet to explore that. But I think the field is open to look into those things. I've seen a few papers of like some very exotic proposals, but they had other problems for which they couldn't be implemented. But I think in principle, it's something that you can do. I've thought a little bit about it, and I think there are some ideas. Of course, you know, the more you add to your system, the more sources of noises and errors you have. So I think you need to have a strong motivation to do it. But I think in principle, you can. Yeah. Yeah.
I think the picture you showed like all of the atoms in your array being excited to the different states.
Mm-hmm.
So, but is it easy or possible to do like a subset of them so that you're
that's
just like local?
That's a good question. We're gonna talk about this in the next few days. So, yeah, that's totally a thing that people are thinking about, and you know, there are some initial implementations. So to do that, it means that you want to shine your lasers to excite to the Rydberg state only locally on some subset of atoms. That is doable, but it becomes more difficult. And especially, let's say that you have your array and you want to address an atom here, an atom here, a subset of atoms, but they're kind of delocalized. The hard thing there is to, if you want this coupling to be homogeneous, and so all of them to have the same thing, then it means that you need to be very good at, you know, shining lasers that are exactly the same. They have the same amplitude. They have the same waist. They're, you know, exactly identical. And this is harder than just shining this big laser that is homogeneous. But there are ways in which people are doing it, and there are some initial implementation. It's something that for sure at some point you want to do, because, you know, when you do a quantum circuit, you might want to have some pairs of atoms that are doing an entangling gate, but not all of them. There are other ways around it that I'm going to talk about in 2 days. But yeah, that is something that people are definitely working on. There are some tricks that you can play to make it more robust. Yeah. Yep.
In terms of the interaction from VIJ
Mm-hmm.
and the Hamiltonian, how long is the coherence time of your system?
What do you mean in terms of you're saying with respect to the typical interaction timescales? So as I was saying, so one timescale that you want to consider. So I was saying that the Rydberg interactions are typically between tens of megahertz to more typically actually towards the gigahertz scale. So it means that the interaction time is on the order of nanoseconds. And one time scale that you want to consider is what is the lifetime of the Rydberg state, which is 100 microseconds. But then you have other sources of decoherence. This is very experiment dependent, so I cannot give you a number that applies to all. But that's certainly one of the limitations we have now, that we need to improve these coherence times. You can have, I think right now, it's typical to have, let's say, 10 microseconds or a few microseconds coherence times when you're in the ground Rydberg manifold. Yeah. Yes, and I mean, yeah, there are some caveats, but I think we're gonna get there. We're gonna see these numbers in 2 days, which is easier. Yeah.
Maybe a nice question. So when you're loading the atoms, said that the reason why there is vacuum frequencies are because two atoms.
Mm-hmm.
So can we not avoid that by using the fermion?
There is actually I want to tell a slide, but I didn't have time. So I'm gonna put some references. There is a technique that is called enhanced loading, where you don't need to use fermions. You can still use bosons, but basically you play some tricks with this molecular potential such that instead of losing both atoms, when you have a pair, you only lose one, and so you have a much higher probability to have one atom per tweezer. And I think the maximum loading efficiency that they've seen for this case is like 90%. Actually, Cindy Regal here has done it. She's the first one who did it. I'm gonna put the references of those papers in the slides so that you can see those. It's actually something very interesting. The reason why not a lot of people are doing it is that it takes more time to do this enhanced loading than it takes to do the normal loading. And so it's a little bit of a game of like, how much do you win in doing that versus in doing the rearrangement. But I think there is still room for improvement there. It's not something that has been super studied yet. So I think we might manage to make it work even faster so that it's actually better. Yeah. Mm-hmm. Good question. So what I've shown you so far is that we shuttle the atoms around before doing any quantum operation. So here you don't really care much because even after you move them, you can cool them again a little bit. And so it doesn't really matter. Even if you do it non-adiabatically, you just do an abrupt move. The only thing you care about is that you don't move too fast such that the atom falls off the trap. So here we don't do either of those. We don't do adiabatic, but we don't even do shortcuts to adiabaticity. What I'm gonna show you in a couple of days is that we now started to do these movements also during the quantum operation. So there you care a lot more about being adiabatic. For now, we've done basically a sort of adiabatic movement. So you start moving very slow and then you accelerate and then you slow down again. I think there are some proposals to do this with some shortcuts to adiabaticity. I'm not sure they've been tried in experiments yet, but there are some ideas on how to do that. I think that would be interesting to probe because potentially you can make this faster. Yeah, I think that's an interesting thing to do. I'm pretty sure that someone thought about that. I can't remember the paper, but there was someone discussing how you can do these movements faster by doing that. Maybe it was you. I don't know. Okay. Okay. Anybody else? Yeah. Acousto-optical deflector. Yeah. Spatial line modulator. Yeah.
How are they different?
Yeah, they're very different. So the spatial line modulator is basically what you have in a projector. It's this liquid crystal screen that what it can do is it can imprint a certain phase profile on your atom. So it's a holographic technique, whereas the acousto-optical deflector is just, you have the crystal, you go through with your beam, you get deflected by a certain angle because of the phonon. So it's a very different type of thing. The difference is, I think the spatial light modulator can do anything. So we use it here to do the array, but you can use it to shape your beam into any formula. They can both create tweezers. The thing in 2D is that if you want to use the same strategy that you used in 1D, but in 2D, it's a little bit more difficult because now the frequencies that create the rows are connected to the frequencies that create the columns. And so when you shuttle atoms, you need to consider that you have these 2 degrees of freedom. So you cannot just do this. I mean, if you, so when you create the array, let's say that you have a hole here. And so you want to move this trap here, this atom here. If you take the frequency that defines this column in the AOD and you move it, you're going to move this one too. So these are now coupled. So the idea of using 2 tweezer arrays is that you now have an atom, a tweezer array that creates the backbone, and that one is static. So you have your array, and then you use the second set of tweezers just to do the movement within there. Okay. Anything else? Okay, perfect.